Diffraction grating. In optics, a diffraction grating is an optical component with a periodic structure that splits and diffracts light into several beams traveling in different directions. The directions of this beam depend on the spacing of the grating and the wavelength of the light, so that the grating acts as the diversive element. The principles of diffraction grating were discovered by James Gregory about a year after Isaac Newton's prism experiments. The first man-made diffraction grating was made around 1785 by Philadelphia inventor David Rittenhouse, who strung hairs between two finely threaded screws. There are multiple orders of the peak associated with the interference of the light through the multiple slits. The intensities of these peaks are affected by the diffraction envelope, which is determined by the width of the single slit making up the grating. The overall grating intensity is given by the product of the intensity expressions for interference and diffraction. A monochromatic light shines on a 400 line millimeter grating. First order line on screen is 20 cm from the 0th order line. If the screen is 0.8 meter away, what is the wavelength and how far from center of screen is the second order line? And now let's proceed to the given. So 400 line millimeter grating, so that means distance between the adjacent line is 1 mm over 400 is equal to 0.0025 millimeter. So the first order line is 1, so m is equal to 1. M1 is 20 centimeter from the distance of the screen. So y is equal to 20 centimeter. And when you convert it to meter, is equal to 0.2 meters. So if the screen is 0.8 meter away, so the L is 0.8 meter, which is the distance of the screen. And now the formula that we're going to use is D sin theta is equals to M lambda. So we're looking for the wavelength. And now let's perform the formula. Let's substitute D, which is the distance, 0.0025 milli, so it means times 10 raised to negative 3. And if the angle is small in the y, angle small to the y is not much smaller than the y, therefore we have to use the tan theta. Tan theta is equal to y over L, which means 0.2 over the L is 0.8. So when deriving the problem, theta is equal to tan become inverse is equals to 0.2 over 0.8. So the answer is, let's look, shift tan is equal to 0.2 over 0.8 is equals to 14. So we're going to angle 14. Now let's go back to the formula. 0.0025 times 10 raised to negative 3 sin, which is our theta is 14 degree. 14 is equals to m, which is 1 times the y. So now let's compute the answer. 0.0025 times 10 raised to negative 3 over times sin 14 degree is equals to, that's the answer. So the answer is lambda is equal to 6.05 times 10 raised to negative m. Now let's proceed to B. How far from the center of screen is the second order line? So B, we want the second order line. So still the distance is 0.0025 times 10 raised to negative 3. The angle is bigger, that means we cannot use the sin theta y over L. So first, let's find out the angle and use the tan theta YL. So 0.0025 times 10 raised to negative 3 times the sin theta over m, which is 2 times the wavelength, which is 6.05 times 10 raised to negative 7 meters. So the answer is, so the sin theta is equals to 0.484. So let's convert theta is equals to sin inverse 0.484 is equals to 28.9. So 29.9 degree. 29.9 degrees. And now let's use the tan theta is equals to y over L. It means tan is equals to 28.9 degree over y is over 0.8. Let's look for the answer. So it's 28.9 degree. So tan theta is equals to y over L, because tan 28.9 degree is equals to y over 8.8. So multiply tan 28.9 times 0.9. So the answer is 0.44 meters. 0.40. Notice that the first order line is 20 away and the second order line is 0.44 meter away. So it is more than twice the 20 because the angle is big.